This is StarTalk. Neil deGrasse Tyson, you're a personal astrophysicist. Got Chuck Nice with me. Chuck.
Yes, sir. What's up, Neil?
All right, we do cosmic queries today.
Yes, it is.
But beyond category.
Cosmic grab bag.
Grab bag?
Yeah.
Galactic
gumbo.
Is gumbo really just trash that was left over when it was invented?
Not when Yvonne Gagne makes it. I told you I'm going to get you some Yvonne Gagne gumbo. Let me tell you now. Hey, boy, I tell you, I'm going to crawl dad in there, boy. Put myself a little there, and you won't know kill. Then also guarantee.
All I heard was guarantee. So this is just, so why aren't we sorting them anymore? They're just random?
No, because they they come in random. Sometimes they come in such a way that,
okay, all right.
That's how they just come in and they make, they're good questions. Let's just throw them all together and let's do it.
And I'll answer what I can.
There you go. All right, this is Jiraj Belangi. And Jiraj says, is it theoretically possible to develop a space drive that would have constant acceleration, hence creating constant artificial gravity?
That's what rockets do.
Okay.
Okay.
But he means continuous, like we're going to Mars.
Yes.
And so you're burning the entire time that you're going.
If you do that, you'll get there very fast. Like, so this 9-month journey that we talk about going to Mars, 3 days to the moon, 9 months to Mars, you know what that is? Mm-hmm. That is aiming for where the object will be when you arrive.
Gotcha.
Fire your engines enough so you don't fall back to Earth.
Right.
Okay? And you need enough energy to cross over to where your destination's gravity exceeds the gravity of Earth.
Right. So it's basically like that planet, when it gets to that, it lassos you and then starts pulling you towards the planet.
It's like climbing to the top of a hill and then you can just roll down,
the hill.
Okay?
Right.
So you're climbing out of the gravitational well of the Earth, and it's getting weaker and weaker and weaker, but as you're getting towards the other object, it's getting stronger and stronger and stronger.
Right.
There's a point where they balance, and if you cross over that point, you just fall towards your destination. Correct. Once you launched yourself with enough speed to get there, there's no engines firing.
Right.
And once you cross over, no engines firing, you just fall in.
Right.
You need your engines again to not crash. Okay.
Right.
Because you're accelerating all the way there by the action of the planet.
Right.
All right. To Mars, that's a minimum of 9 months. If instead you accelerated the whole time, then you still want to slow down. So you'll accelerate till you're like halfway there, then turn around and then decelerate the rest of the time.
Captain, we're approaching the planet. Fire the retrorockets. You got to fire the retrorockets.
Yes, except this would be a sustained thing. And that way you would maintain a certain artificial gravity, because an acceleration of a rocket is an exact mimic of being on a gravitational surface.
So the only sci-fi show I've ever seen that does, and I recognized it from you telling me exactly what you just said years ago, it's called The Expanse. And I had so much respect for them because they show a ship headed towards a planet, and the engines you see first firing as it's moving towards the planet. So it's like the entire time that they're showing you, like, oh, they're headed to whatever planet. And then they show you, and it looks like the ship is going in reverse.
Oh, interesting.
Yeah, but exactly why you said, because they're firing the rockets to slow down. To approach the planet.
Correct.
So cool.
But there's another interesting fact here. While you are firing rockets, there is a force operating on you that you will not be able to distinguish from an ordinary gravitational force. This was deduced by Albert Einstein in what's called the Equivalence Principle. An accelerating rocket is indistinguishable from you sitting on Earth with Earth's acceleration of gravity, if the two accelerations are equal.
Right.
There's no experiment you can perform other than looking out the window to know if you're in a rocket or sitting here on Earth in a box.
Right.
Okay, so now, what's that movie that had moon pirates?
Oh, that was called Ad Astra.
Ad Astra.
That was Ad Astra.
If you're going to use the phrase Ad Astra, you better get your stuff correct.
That's right.
Okay, Ad Astra means to the stars in Latin.
Right.
This is a deep phrase that we've been using in the space community forever.
Right.
And interestingly, it's on the state flag of Kansas.
For the tornado state, that makes sense.
Dorothy,
That makes sense for the tornado state. I was launched at Astra. Woo!
So they would show these rockets firing, and you go inside the ship, and they were all weightless. No.
That wouldn't work.
There's this misconception that being in space
makes you weightless.
No.
Right.
No. If you are drifting in space, as our space missions do, they're sent in motion, and you're drifting towards the crossover point, and then you fall in. Oh, there you go. You're weightless that entire time. But as long as you have on rockets, you are not weightless at all.
Look at that.
Yeah.
Super cool, man.
Yeah. So, so you could do it, but sorry, getting back to the question.
Right.
You need filling stations along the way.
What?
If you're going to drive straight from New York to LA,
that's right.
How big must your gas tank be?
Well, yes.
Okay. So we have gas stations along the way. So if you really want to accelerate to your destination through space, you need filling stations parked throughout the solar system.
Right.
And you reload and keep going.
Right.
But we're not there yet.
Or like in Star Wars, where they have the ship that is part of another ship. So there's one ship that gets you to hyperspace, but then when you come out of hyperspace, your ship leaves that ship, and then you can just ride normal.
Okay, so something else did all the heavy lifting. Yeah. Okay,
cool, man. Very, very cool, Jiraj. Thanks for the question. Here's Ryan.
Oh, and just while I'm there,
go ahead.
When you're in orbit, you're freely falling towards Earth. There are no rockets keeping you in orbit.
Yeah, you're just falling around the Earth.
Around the Earth, and so you're weightless there. It's not because there's no gravity in space.
Right.
Right. We have it's a delusion, not a delusion. We've been misled to think that the act of being in space is synonymous with being weightless.
No,
that
it's the same as when you're on that, what's it called? The Vomit Comet? What's that thing called?
Vomit Comet, yeah. The airplane.
Yeah,
it goes into a controlled, into a parabolic dive where you're falling towards Earth.
Exactly.
It's basically, for that short period for that short bit, it's sort of orbiting Earth.
Right.
Did you have physics in high school?
They taught it in my school.
Okay, I should have. Did you learn physics in high school? Sorry.
Yeah, those are two different questions.
One of the things you learn is that a projectile has a parabolic arc.
Right.
Okay. And there's a formula for a parabola, and you can solve how far, neglecting air resistance, you can know how far a projectile will go.
First use of computers.
Yes, in fact, it was. For the military.
For the military.
They want to know where the bomb's going to fall.
Okay. You got to be able to figure out the trajectory of mortar shells.
Turns out, it's not actually a parabola.
Oh, okay.
It's very close.
Right.
But it's not a parabola. It is the segment of an orbit, an elliptical orbit.
Gotcha.
If the entire mass of the Earth were at its center.
That makes sense.
Okay.
That is so cool.
Yes, it's completely cool.
That is so cool.
So you take all the mass of the Earth, collapse it to a point in the center, and watch this go in orbit around
that point.
Around that point.
That's right. That is so cool.
Okay. So, but it doesn't succeed because Earth gets in the way.
Exactly.
But the forces controlling it is what's the mass of the Earth and what's its distance from the center of the Earth.
Right.
That's all that matters.
That's so
cool. You collapse all the mass there, and then you have it.
Fantastic.
Yeah. So even when you're
in like the space station, you're just falling around the Earth.
Falling around the Earth.
Very, very
Correct.
cool. Very cool, man.
All right.
All right. Here's
Next.
Ryan A. Ryan A. says, "Hey Neil."
Is he witness protection there? He's Ryan A.
Yeah, okay. Exactly. He says, "Hey Neil, and maybe Chuck. Oh, would you know something I don't know, Ryan?" He says, "Hey Neil, maybe Chuck. Ryan from Toronto here. My question might be obvious, but time dilation has been messing with my mind."
As it should. But
Exactly.
No one should be comfortable with time dilation. Okay.
Right?
Mm-hmm.
Yeah. Once you said that a photon doesn't experience time. It's born and immediately is destroyed. If a photon from somewhere in the galaxy is born, and over time it redshifts as we know photons do, how can it both experience a redshift but also be destroyed immediately after creation? Thanks. Love the show.
That's a great question.
It really is.
I don't know that I have a good answer for that.
I do.
Because that's how it is.
Because that's how photons roll. Okay?
So what he's saying is if the photon that's emitted is different from the photon that you detected or destroyed at the end of its path, then something happened to the photon. So if something happened to the photon has to be temporarily aware of that in some way.
Right. Wow, you asked that question better than he did.
I'm thinking that's what he means. I'm pretty sure. Pretty sure. Yeah. So we see this. The question is, what does the photon think happened?
Right.
Now, since it's emitted at one wavelength and detected at another, I got to think about that.
That's something, huh?
Because the photon would have to say, I'm redshifting. But to even be able to say that, time elapsed for you.
It's exactly.
Because you was something yesterday and something different tomorrow.
Different. Right.
Yep.
That's pretty wild.
No, I don't have a good answer. You know who might have an answer is Jana. Jana, friend of the show.
Yeah, exactly.
She's a cosmologist.
Somebody call Jana.
We got the hotline.
Where's the Jana hotline, please? Can we get Jana on the phone, guys? Can we get Jana on the phone?
I have a red phone at my desk. Did you know this?
And is that for Jana or is that for somebody to put that mustache in the sky to call you?
Mustache in the sky. Emergency.
We have a cosmic emergency. Put the mustache in the sky.
Mustache. You know, if this was 150 years ago, everyone would have a mustache, and then no one would be talking about my mustache.
True, that's true.
You'd be true. You know, everybody in the Civil War had a mustache.
And weird ones, too, with handlebars and all kinds of crap.
Okay.
Yeah. All right, well, listen, that's a very good question, Ryan A.
And, I'm sorry.
And who knows? Who knows what the answer is?
I have to ask the photon. I'll get back to him.
Learning the complexities of the universe and the intricacies of astrophysics is like learning a completely new language. Take it from me, I've had a front row seat to one of the greatest teachers of our generation, and there's still so much to learn, and I love it. You know, with any new language or subject you're looking to learn, you need a great teacher. And that's why we're thrilled to introduce today's sponsor, Babbel. One of the top language learning apps in the world, providing you with access to learn up to 14 new languages from the convenience of your phone. At just 10 minutes per lesson, Babbel makes it incredibly easy to get started on your new journey, no matter how busy your schedule might be. Now, Babbel lessons are created by over 650 real language experts, so you can learn practical, real-world conversations in no time at all. Now, I live in a heavily Spanish-speaking community, and I've taken it upon myself to learn Spanish so I can get a little closer to my neighbors. Plus, I really don't want them talking behind my back without me knowing. Now, whatever your reason is, you can try Babbel today, risk-free, with a complete money-back guarantee within your first 20 days. You'll get 60% off when you sign up. As Neil once said, there is no greater education than the one that is self-driven. So, let's get you started today on a path to learning something new with Babbel. All right, that's it. Let's get you back to the show. Vamos.
All right, this is Amar Shah. And Amar Shah says, greetings, Dr. Tyson, Lord Nice. This is Amar from Sydney, Australia. Is it possible mathematically that our universe is on the other side of a black hole? And could there be more universes on the other sides of black holes? I think, does he mean our galaxy? Because
I have a book on the shelf that goes through the mathematics of what's on the other side of a black hole.
Of a black hole.
Right.
Right.
And if you fall in, your time slows down relative to what you just came from.
Right.
And you'll see the entire future history of the universe unfold.
Right.
As you go down and emerge, a whole other space-time opens up in front of you.
I gotcha.
The mathematics of general relativity gives you that.
Right.
No one has tested this, but general relativity works in all these other ways. And this is a prediction of something that has worked so well.
Mm-hmm.
It's intriguing. Certainly worthy of at least sci-fi treatment before we get actual data. So the universe that has the most universes is the universe that has the most black holes.
Right. Now, is it a different universe or is it a residual universe?
Call it what you will, but there's you can't go back and forth.
Of course you can't.
So by our operational definition of universe, you're in another universe.
You're in another universe.
And don't denigrate it by calling it residual or universe light or dwarf universe.
Okay. I got you.
All right.
I didn't mean to, didn't mean to PO the universe.
No telling what'll happen.
Well, that's very cool. So mathematically, it does work out.
Yes,
that's how
it does.
works.
Mathematically.
All right, cool. This is Eduardo.
Oh, by the way.
Yeah.
The horizon of the universe.
Right.
This is beyond which you cannot see.
Okay.
Has all the same properties as the event horizon of a black hole.
Oh, so cool. So what we see is the edge of our universe that we can observe has all the same properties as the
same mathematical properties as the event horizon of a black hole.
Wow, I didn't know
so
that.
We would be living evidence of a universe inside a black hole.
Would be. That's crazy.
It's freaky.
Yo, that is. Damn.
That's good.
Somebody
right?
get me an edible.
No, apparently you didn't need one.
This is true. This is true. It was sufficiently fascinating enough that I did not need any assistance.
Correct.
And having my mind blown.
A no assist fact.
Yeah.
Mm-hmm.
That's cool. All right. This is Eduardo Mancilla. Hello, this is Eduardo writing from Mexico. Or should I say, hello, this is Eduardo writing from Mexico. Now, normally I would reserve that for our friend from Monterrey, Mexico. He says...
you heard that dinosaur joke? It's a stupid joke. So I was giving a public talk, and I was describing the 65 million year ago event where Earth got hit by an asteroid, and we found where the crater is. It's off the tip of the Yucatan Peninsula.
Okay.
Of Mexico. And I thought it'd be cute and say, the Yucatan Peninsula of Mexico, but that's not what the dinosaurs called it because it was. And then someone in the audience, they called it Mexico.
Stupid.
It was like stupid funny.
Yeah, it is.
I mean, clearly they spoke Spanish.
Right.
Exactly. And they would pronounce it correctly.
All right. So Eduardo says, I saw a video on strange matter, but I didn't quite understand what exactly that is. Could you maybe talk a little bit about what it is and how it forms? Strange matter.
Yeah, I'm not up on the very latest there, but there's actually good precedent for having this mysterious thing happen in our particle accelerators. And we say, we can't explain this. There must be some particle we haven't discovered yet accounting for this inexplainable stuff.
Ooh.
For this behavior of the other particles, they're responding to something that we can't see and don't know how to figure out how to detect it yet.
Right.
So let's invent the idea of this particle. Doing that has enabled the discovery of multiple particles. Assume something's there.
Right.
What would its properties be to cause all the confusion that it does?
Right.
Let's look for it.
And then look for it.
And we found it.
Look at that.
The neutrino was one such particle.
Look at that.
All right. There was a reaction of particles, and at the end, the charge all worked out, but the momentum didn't add up. So we have a law of conservation of momentum. It's never been violated.
Right.
All right. It was missing some momentum. Way to go. All the same, we took account of all the particles.
Right.
And somebody said, a particle must have taken away the momentum. I don't know where. Go look for it. And we knew it didn't have a charge, so it was called little neutral one.
Little neutral one.
Neutrino.
Oh, cool.
Yeah. So there are things we cannot explain. Dark matter, dark energy. There are these phenomena in the universe where we are kind of, I don't know, I want to say we're giving up, but we'll say, we don't know what it is, okay? Just call it anything, okay? Is it some new kind of matter? Is it strange matter? Is it, and there's a whole catalog of names for these particles that are not yet discovered. And many of them are fanciful.
Wow.
So it's like a zoo.
So is that like missing spaces in the periodical chart?
Oh, very nice.
Yeah.
Chuck.
Okay, cool.
Very nice analog there.
All right.
Because that's complete now.
Right.
You know, on many things you can say, we got this.
We got it.
Move on to the next problem.
Right.
But we got this.
Right. But there was a time when they had to leave a space.
They left the space.
Hey, we know something going to go there.
Right. And, you know, one of them was discovered, I forgot exactly when, but it was not discovered in nature. We had to make it.
Oh, right on.
Okay. Do you know the word for when you make something?
Manufacturer.
Yeah. Tech.
Oh.
Technology is you made it.
Right.
You didn't get it from nature.
Right.
Okay. We forgot that because it applies to everything today. Tech. Okay. So it's called technetium.
Technetium.
Yep. We made that. Made that element.
That's pretty cool.
So of all these hypothetical forms of matter,
Right.
all right, one of them has been named for a variety of quark
Okay.
that we know. Quarks have fanciful names.
Yeah.
Okay. There's an up quark,
Right.
a down quark,
Right.
a strange quark, a charmed quark. Okay.
Well, a wine quark.
Wine quark. Quark.
Oh, quark.
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 Okay. Okay.
Quark. So, and the quarks make up our nuclear particles.
Right.
Okay. So there's an up, down, top, bottom, strange, charmed. Okay.
Okay.
So the up, down are the quarks that make up protons and neutrons.
Okay.
They have heavier components in the universe that we find in accelerators, but we don't encounter them every day. So all the particles that we know and love have versions that exist at a higher energy level.
Gotcha.
So our quarks are up and down. The next level quarks are top and bottom because they're pairs. And the next level quarks are strange and charmed.
Gotcha.
There's 3 levels of electrons as well,
Okay.
3 different kinds of force carriers. So this is what we call the standard model. Yeah, we chatted about that with
Brian Greene.
Right?
Yeah.
It's been hypothesized that the strange quark, under certain conditions of pressure, temperature, would manifest and be the predominant particle in the object.
Okay.
So it'd be strange matter possibly making a strange star.
Gotcha.
Yeah, but don't overinterpret the word strange. It's just a word to describe a variety of quark. And you know where the word came from?
Top and bottom quark from
No,
the gay
quark,
community.
The word. Stop. Cancel him, okay?
No, what are you talking about? I'm an advocate, okay? I don't care what you're talking about. I'm an ally, so don't cancel me.
The word quark comes from James Joyce's Finnegan's Wake.
Really?
Yes.
Oh, okay. How so?
Because we found that there were 3 quarks in the middle of the proton and neutron.
Right.
Okay. 3. And there's some rhyme in Finnegan's Wake that says 3 quarks for muster mark. And so Murray Gell-Mann, who's one of the original physicists to think about what the particles are in the
tiny stuff.
In the tiny particles. He had that phrase in his head. And then he says 3 quarks for muster mark. And so it was 3 because the number 3 matched. Okay. Except there's more than 3. There's like, you know, with the 2 varieties times 3, there's 6 kinds of quarks. So the numbers in the end don't match up.
Well, he didn't know.
He didn't know. He just started. He just began the investigation.
Oh,
but the word quark stayed.
Okay.
Mm-hmm.
Yeah. It's a dumb name. All right.
Well, you can't say, what does it look like? Right?
That's true.
I mean, in my field, we see a nebula that looks like a tarantula. We call it the Tarantula Nebula.
Right.
We see another nebula that looks like North America. It's called the North American Nebula.
That's so crazy.
If you see a quark, what are you going to say it looks like?
Well, there is nothing that
That's what I'm saying.
There's nothing to say.
There's nothing.
You can't.
Right.
Right. Oh, that's cool. All
okay.
Right. I take it back.
We do have that problem.
Muster mark.
If you ask me, how big is the universe?
Well, how big is the universe?
It's as big as... End of sentence.
There you go. Because how could you know?
Right. You can't.
It is the biggest.
You can't compare it.
Yeah. There's nothing to compare.
I can tell you how many feet will go across it, but that's
still doesn't make it.
There's no reference frame for it.
Right.
Mm-hmm.
Okay.
Good. Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
If you weren't the director of the Hayden Planetarium, what do you think you would be doing? What?
Okay, but this had to be another universe. It wouldn't happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up.
Let's move on to Maurice van der Linden. He says, "Dear,
Is he from the Netherlands or something?
yeah, it could be
Van der Linden. Yes.
Van der Linden from Rotterdam. Hello, this is Maurice van der Linden from Rotterdam.
They don't speak like that.
I don't know what they speak like. I mean, I've been there several times, but I still don't know what they speak. They speak Dutch, so they sound, Anyway, he says, "Dear Cosmos connoisseurs, Maurice from the Netherlands here."
Oh, from the Netherlands.
And he was from the Netherlands. Wanting to know more about gas giants.
Mm-hmm.
Why are they named that way? Oh, come on, Maurice. Come on, Maurice.
No, maybe let's keep reading.
All right, I'm going to keep reading. All right. Don't they okay, look at you, keep reading. Don't they have a solid core and gaseous atmosphere, the same as terrestrial planets? Love the show, keep it up. So in other words, why can't we just call them, bigger atmosphere planets?
Okay, because...
Here we go. No, when you get the Tyson neck roll,
don't make me do this.
You know you about to get red. Here's why. Let me tell you why.
The difference is, on Earth, Earth's atmosphere is to the solid planet what the skin of an apple is to an apple.
Gotcha.
Whereas on the gas giants, their atmosphere is to their solid core what a peach is to its pit.
Okay. That makes sense.
Okay.
I got what you're saying. Because, I mean, we have...
Our
atmosphere is gas. So...
It is gas.
It is still gas, but...
It ain't much of it.
But it has nothing to really do with what we are, if you were to really look at it.
Well, structurally. I mean, it matters for our life and our ecosphere and everything.
No, I'm saying if you were to take it away, we would still be a giant rock floating in space.
Correct.
There you go.
Correct. You take away the atmosphere of the gas giants,
right?
They'd be unrecognizable.
You got nothing. Right.
Correct.
Right.
Correct. So a peach to its pit or smaller than a pit.
Right.
I'm trying to think of what's a good analog there.
Like an apple to a seed.
Yeah, but that's more seeds, and I have to
more
then
seeds. I know what you're saying.
Right.
You're such a scientist.
I was thinking,
you know what I mean?
okay,
Seriously,
lately,
you just can't let an apple have one freaking seed.
That's
Okay,
correct.
everybody know what the seed of an apple looks like. You will not. No, you're like, no, you cut the apple open, and you got 6 seeds in there. So we got to have one seed.
I'm educator man.
Okay,
and I've had some avocados lately.
All right.
They had really small pits. So somebody's breeding them things to be little.
Yeah.
Like when we grew up.
No, they were giant.
Giant.
Yeah.
So maybe avocado one day would just have a tiny little pit and it'll all be flesh on the outside. That'd be like the gas giants.
Right.
Yeah. So he's right to think, yes, they have a solid core.
Right.
But it's a tiny thing way down inside.
Right.
Mm-hmm.
And let me ask this on
for all of them.
Follow up from Maurice. No, though. Is that tiny core solid because of all the pressure that the gas makes?
They are made out of the same ingredients as we are.
Oh.
Let me be precise.
Okay.
Okay?
All right.
The original nebula that formed the sun and the planets.
Okay.
It's gas.
Right.
mixed with heavy elements,
Right.
but they're just gaseous heavy elements.
Okay.
The gas giants, when they form, where do the heavy elements go?
To the center.
Thank you. And they make a solid mass there.
Uh-huh.
The lighter elements go up to the top, especially the hydrogen and the helium, and it has enough gravity to hold on to them. They're moving fast, but they're not going to escape because the gravity is strong.
Gotcha.
For our Earth, where do the heavy elements go?
To the center.
How about the gas? The lighter gases, the two lightest gases are hydrogen and helium. They're moving the fastest at any given temperature.
Right.
It's a fascinating law first discovered by James Clerk Maxwell.
Okay.
We should talk about that.
Oh, James Clerk Maxwell?
No, to put his Maxwellian distribution of velocities.
Ooh.
Let's do an explainer on that.
We will.
No, it's very cool.
All right.
Really cool.
I'm about it.
Okay, you got it?
Cool.
Okay, put a pin in that.
Okay.
All right, good. So we're here. We're trying to hold on to the hydrogen and helium
Right.
the way Jupiter, Saturn, Uranus, and Neptune did, but we can't because our
Well,
gravity
we don't
is
have enough
strong enough,
gravity.
and it all just
And
escapes
it
back up.
goes out.
Okay?
That's really cool.
So we're stuck with the heavy gases, oxygen, nitrogen,
Right.
and carbon dioxide.
Okay.
Right.
So that's how that works.
That's how that works.
Excellent.
Yeah.
Oh, man, that was great. Okay, cool. I like when those simple stuff.
And of course, within the solid core,
Mhm.
the heavier stuff is in the center of the solid core,
Right.
right? And what's in our solid core? We got iron,
Iron.
there. And iron is heavier than,
Everything.
it's heavier than the rocks.
Right.
Rocks float
Compared to iron.
compared to iron. Yeah, all right.
Super cool, man. This is Vasco Vukov. And Vasco Vukov says, hello, Dr. Tyson, Mr. Nice. This is Vasil Vukov from Sofia, Bulgaria.
Nice.
We're trying to find aliens, but if we want to hide from them, what should we and could we do even if they point their sensors straight towards us? How stealth could the Earth possibly be?
I love that. Okay, so now watch. Okay,
All right.
you ready?
Go ahead.
Okay. Let's go back in time.
Mm-hmm.
TV signals.
Right.
The reason why there's old timers, everyone else just won't care what I'm about to say.
Mm-hmm.
In the day, you could get radio stations from cities that were far away, but you wouldn't get TV stations.
Mm-hmm.
TV waves, you have to be in a direct sight line to the television transmitter.
Okay.
So you have to have a transmitter everywhere for TV.
Mm-hmm.
So TV was very local in the day. Radio waves, okay, especially shortwave, but also AM radio, its waves had the right frequency to reflect off the ionosphere of the Earth.
Ooh.
And it could send a signal beyond Earth's horizon.
That's crazy.
Some would leak, but others would bounce back.
Right.
Point is, these modes of communication had leakage, especially television waves.
Mm-hmm.
So someone eavesdropping on Earth, and they're, let's say, 80 light years away, they're getting the earliest radio signals that have been emanating from Earth at the speed of light.
Good evening, Mr. and Mrs. America, and all the ships at sea. Dateline.
And there's Howdy Doody.
Right.
There was, and then the TV signals would start coming in. Early TV, the honeymooners.
Uh-huh.
And if they want to decode our civilization.
Right. They think that we're all abusive, who like to threaten our wives with violence.
With violence by
Nah.
to the moon.
To the moon.
And that's when people laughed at that.
Right. Exactly.
Right. I think they left because she was defiant, even in the face of
Right.
that
Exactly.
threat of violence.
Oh my God, you are so funny. You're gonna beat your wife, huh?
Right.
Yeah,
It's
exactly.
crazy. It's a crazy times.
It's been crazy.
Crazy times. So that's how they'll learn how men and women interact. That's their benchmark. So this continues throughout all the sitcoms and all the TV. And they'll see the war broadcasts and everything.
And then they get right up to Puff Daddy and they goes, nothing has changed.
No, they get to the 1980s and signals start disappearing.
Uh-oh. What the heck is happening?
People are using cable.
That's right.
Okay, so one of the earliest shows, which I feared would be first seen by aliens, but I think we're protected, is Beavis and Butthead.
Right.
That was MTV, and you got that via cable.
Right.
Okay, that was not transmitted into space.
Oh, that's a shame.
You want the aliens?
Let me tell you something. The one thing I want the aliens to see is...
Are you threatening me? I am the great Cornelio. Cappuccino.
So a lot of what's happening today is protected from leakage for that reason.
Right.
Because it's
a closed system.
It's a closed system. It's cable.
Right.
Okay.
Gotcha.
So that's my first point. Second point, here's just an interesting fact. If you're communicating through space and you have a signal, you don't want anyone to intercept it.
Okay.
You want to encrypt it.
Right.
Okay.
Yeah, well.
The perfect encryption is so well encrypted that it is indistinguishable from the din of radio noise in the universe.
Oh, that is awesome.
It is completely because think about it. Think about it.
You're using
Think about it.
Okay.
If there was something about your signal that was different, then I would know somebody created it.
Exactly.
Okay? So you need something to encrypt it so that it looks like noise, and you have the noise decoder on the other side.
Look at that.
Okay?
And when you say noise, you're talking about the cosmic microwave background.
I need all of the radio noise in the universe.
In the universe.
Okay? If you take a radio antenna pointed anywhere, there's like noise.
Right. Of course, yeah.
Okay?
That's the
static. It's the static.
Yeah.
Okay? So if I see something that doesn't look like the static, there's a signal there. Even if it is encoded,
right?
I know there's a signal there.
Yeah, because it's different.
It's different from the static.
Right.
So the perfect encodings would be indistinguishable from static. So if a planet wanted to hide from alien eavesdropping, they would make sure that all signal transmission was so thoroughly encoded that it was indistinguishable from static.
Like the noise of the universe.
Correct.
That's great.
Yes.
That is really great.
Yeah.
I love it.
Yeah. And now it's a little tough because you might have more noise here than somewhere else.
Right.
That could give you away.
Right.
Exactly. There's the background in, and then there's a bright noise spot here.
So there's an anomaly of
noise. Of noise. Yeah.
Right.
So you have to figure that one out too.
Yeah.
But
that's cool though.
Yeah, it's very cool. Another way to hide from aliens?
Yeah.
You get one generation of astronomers to send a plaque out into space.
Right.
Intended to be read by aliens. This is a plaque from Pioneer 10 and 11.
Right.
Which was launched in the 1970s. And some of this iconography was also used for the Voyager missions.
Right.
But notice at the bottom, there's the solar system.
There's the solar system. There's the sun.
And Mercury, Venus, Earth. And Earth, there's a line coming from Earth that shows where this spacecraft came from. Because this is a life-size of the spaceship relative to the two human figures. Yeah, exactly. Okay. So you get one generation to try to talk to aliens innocently, not knowing the aliens are evil. They're going to come and suck our brains out.
Right.
But let them show a 9-planet solar system.
Right. Yeah.
This one has Pluto.
Right.
They're going to come looking for us because this is our return address, by the way.
Right.
The spider diagram, that's our distance to pulsars in the galaxy. And you can triangulate on that and come right back to our vicinity.
Why would we do that? Why would we ever do that? That is so.
It seemed like a good idea at the time.
That's insane.
I know you wouldn't give your email to another human stranger in the street.
That's like going on vacation and putting all your plans on social media. Hey, guess what? We're leaving on the 10th and we'll be gone for 2 weeks. That's a perfect time to come rob my house, people.
So now they come back looking for a 9-planet solar system, and ours is not that.
Well, okay.
And the reason why would they not think it? Because Pluto is represented in this
as a planet,
as the same size as like Mercury and other objects here, and it's just not.
Guys, we only see 8 planets here. We got the wrong one.
There you go.
Got the wrong solar
system.
Nothing
to see here.
Nothing going.
Keep going.
All right. Except for that one planet with all the trash out on its front lawn. What is that? What's going on there?
No sign of intelligent life. Returning home.
All right.
The planet Zebula.
All right, this is Letitia Davis. She says, hey, this is Letitia Davis from Conway, Arkansas. So,
nice.
How many early cosmic discoveries were made by curious observers with no formal training? Is the frontier still within the reach of amateurs, or has science advanced too far for a layperson to contribute to the cosmic perspective?
Love that.
Wow, look at that.
Very good. Very good.
All right, Letitia.
So, let me give something that's not an answer to that just yet, because I just want to put it out there. I wrote an essay many moons ago called Stick in the Mud Astronomy. I think it's online. Stick in the Mud Astronomy.
Okay.
If you have a stick and you put it in the ground,
Right.
what can you deduce about the operations of the universe from just
that
a stick in the ground? Okay, you can invent a sundial. You can track rising and setting points of the sun on the horizon and the moon and all of this. Okay, so you can do quite a bit. It was an homage to ancient peoples who didn't have telescopes.
Right.
There's a whole essay on that called "Stick in the Mud Astronomy." All right, without access to frontier telescopes, you're not going to discover dim things.
Right.
Because you're just not going to ever see
them.
Can't see them. However, there are more amateur astronomers in the world than there are professional astronomers. Okay?
Right. Yeah.
And they all have like backyard telescopes. That's fine. Very accessible. They're looking up all the time. Amateur astronomers have famously and historically discovered comets.
Right.
Discovered supernova, although we have supernova surveys now that are very efficient. You might not be in line for that. But if you see something, say something. Okay? We have a clearinghouse because phenomena that comes and goes, we don't know about.
Right. Right.
We can't, I have a telescope for one night and I'm looking and I go home. That's why we have the Vera Rubin telescope, which is basically going to be taking video of the universe, of the whole sky. So you can watch in case something shows up and goes away or disappears. You know what else we'll discover? Every one of Elon Musk's satellites coming across. That'll contaminate the data where we're trying to find out if there's an asteroid with our name on it. So I'm a little worried about that.
So like Elon. So like him.
So what else you can do is you can, and there are coordinated groups that invest this effort. There are asteroids where we don't know how big they are. Okay? We don't have good sort of radar to asteroids.
Right.
So if we think an asteroid is going to come in front of a star and blot out its light, and you have people lined up on Earth to watch this, because how big are asteroids? There's 100 meters across, a few kilometers across, mile across, whatever. It's not thousands of miles across.
Right.
So you line people up on Earth, and some will not see the light of the star dim.
Right.
And other people will.
Yeah.
On each side. So only a narrow path of people will see the light dim. And that can tell you the size of the asteroid. But there are not enough amateur astronomers to do this. So everybody's got to line up, watch the object, keep good time, and do this. So yes, there's still things to do. But also, we have this citizen science projects. We're awash in data.
Yes.
And we say, we're looking for this, help us. I mean, we might put AI on it, but sometimes the human touch matters. And because not all AI is human yet. And so, yes, there are ways you can still contribute.
Very cool. There you go.
Okay, last one, real quick.
All right, this is Sharahi Ravi, who says, greetings, Dr. Tyson, Lord Nice. Currently reside in Dubai, United Arab Emirates. I am a researcher and a graduate student in astrophysics. What possible aspects of our current model of the Big Bang Theory do you feel will be revised, considering the contradictions to the same by the latest James Webb Space Telescope observations?
Yeah, so the Big Bang is supported by so many different lines of evidence that if our galaxy models don't match what we see, chances are it's a problem with the galaxy models.
It's the models.
Yeah.
Right. Not the Big Bang itself.
Not the Big Bang
it's
itself.
The way we've
The galaxies
modeled
are
them out.
embedded within a much larger matrix of observations and data that have been affirmed by measurements over decades. So we think we understand galaxies. The whole point of the James Webb Telescope was to observe galaxies being born.
Right.
Because we don't fully understand that process. If we take what we think galaxies should be like and they don't match it, you don't say toss out the whole Big Bang. You say maybe our understanding of galaxies is flawed.
There you go.
But saying our understanding of galaxies is flawed is very different clickbait from we need to rethink the Big Bang.
Right.
And so that's what we're all caught up in here.
Exactly. Okay.
It's clickbait.
Right. That's it.
That's what do you expect?
Yeah, exactly.
It's
the same as the Bat Boy headlines, you know.
Oh, from the old
Remember
days.
from the old days?
Well,
Bat boy found. It's like a boy, half bat.
right. So I forgot all about those. Yeah.
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 That was the original clickbait.
Yep.
All right.
All right. So that's all we have time for, Chuck.
All right. Well, that was fun.
Knock out another one there.
That was fun.
Okay, got from all over Sydney,
Everywhere.
and the Netherlands, the Netherlands.
We're global, baby.
All right, I'm liking it. Always good to have you, man.
Always a pleasure.
All right, this has been a StarTalk Cosmic Queries from my office here at the Hayden Planetarium of the American Museum of Natural History. As always, I bid you to keep looking up.